Hector, what is this? Hi, this is Hector, your AFM expert on Nanosurf. Has your PI been giving you headaches lately? Then I'll show you how to use our Python interface to control your AFM with one of these. And then your situation will no longer be this, but this. Usually, this is how an AFM works. You have the probe, the scan head, the controller, the computer, and the software. The question is, how to replace this moving the tip in a predefined trajectory for following what the gamepad says? The answer is that we use Nanosurf Python interface. And instead of connecting the gamepad to the computer, we read its inputs directly from Python. But now another problem remains. In a normal operation, there is a stream of data between the scan head and the controller, and packets of data between the controller and the computer. This is not sufficient to operate the AFM with the gamepad, because when we request to move the tip and request back the XY position, we are sending requests one point at a time, and the interface is designed to operate with packets of data. So it is very slow. The problem is that the interface is not designed for streaming data. It's designed to send lines of data. So we have two alternatives here. Either we program again the FPGA and design a new communication protocol, or we figure out a way of transferring the information directly from the controller to the Python script. And in my case, I'm going to go for this last option because I'm more comfortable building devices than coding FPGAs. So the solution I found is that I can output the XY set position of the probe as voltages on the controller interface. I can read these voltages with an Arduino board, and I can have this board streaming this data back into Python. It is much slower than the bandwidth the AFM can provide, but it's a decent solution instead of having to work with the FPGA code. So the final setup looks something like this, with the Arduino in between the controller and Python. And the code for Arduino simply reads 3 analog voltages and writes these voltages to the serial port, with one small detail, or very important detail actually. We don't read the voltages all at once, but we intercalate right into the serial port. This is because this particular Arduino board only has 2 analog to digital converters. So if we ask the converter very frequently, it's going to give us the same value. It doesn't have enough time to actually change the reading for a different channel. So I will show you first how the script operates, and then I will show you what's happening inside. The idea is that you have your Nanosurf Studio software running. Your probe is close to the surface, and laser is in good position, and you're running your Python interpreter, in this case Visual Studio. When you run the script, a graphic user interface appears and immediately starts tracking, recording what the AFM is doing, XYZ movement. This top part of the user interface lets you choose which function corresponds to which button in the gamepad. For instance, I can map the X button in the gamepad to initialize a scan, one by one micrometer scan or a spiral scan or a full scan. Then we have this bottom part which is to visualize the data that has been acquired, and this right hand side panel to change the parameters of the visualization. If we want to see the full scan area, or if we want to focus in one part, or if we want to change the set scale. Here it seems as if the Arduino is skipping some points. This is because we have to convert the XY set position several times, and on the conversion we lose resolution. So imagine we have a full range of 100 micrometers. Then we convert this to -5 +5, which is the standard output of the controller. Then I have to convert this from 0 to 5 volts, because this is what the Arduino accepts as an input. And then inside of the Arduino, the ADC makes a conversion and turns this 0 to 5 volts to 0 to 1023 integers. This means that roughly we get each pixel is about 100 nanometers large. If we want to get a higher resolution, then we need to change this scaling and limit how much is the range that this script can see. These are included in the code, and it's possible to change it, but I leave it out as a feature. It will be included only for people that want to really tinker with the script. I want to stress something here, and is that the way the data is being captured, it's XY set plus a timestamp. This timestamp let us reconstruct the movement of the tip. This is something that commonly is not being used a lot, but it lets you play with the visualization in a way that you can see which parts of the image were captured when. And in cases where you may be using your tip to modify the surface, you can see as a sort of movie what the tip was doing at which moment in time. I think this is an interesting concept, something that I will probably explore more in the future. I think something that is nice here is also how we can use data that was taken in different moments in time to obtain the final image. This is nice because we can choose if we want to do this or not, because we have the timestamp. It is very easy to select if we want to visualize together the data that was captured during the whole session, or if we want to visualize only the last 10 minutes, because that's when the imaging conditions are better. I think this is something that hardcore AFM users will appreciate as something really useful. So this is how the script operates. It has one thread that is reading the serial continuously at the fastest speed possible. This same thread is also updating the set data or the set array, and is saving all the data to a file in a way that the file is always increased. So if the script closes or we decided to stop, the data is not lost. Then we have the GUI thread, which is where we can visualize things and we can configure what the gamepad is doing. This thread has the map, the ability to map the gamepad to different functions, and also set the plot properties. And it has two threads inside. One is updating the plot. This is happening about half a second. This is why sometimes you can see some delay between what the AFM is doing and what is being represented. And it has another thread that is listening to the gamepad. How fast is listening to the gamepad depends on where do you think is doing too much or where do you think is lagging behind. And then there is define a series of functions that can be called from the GUI when you press a button in the gamepad. These are orders to the AFM. For instance, approach, start an image, or execute a specific spectroscopy routine. For instance, go up and then go down until reaching certain set point, and then retract again. And any other function that you can think of. I left these instructions in the code so you can play with them or add your different routines here. It's important to note that I decided to separate the thread reading the serial port and the thread for the GUI because the thread for the GUI is kind of slow. Or at least the library I was using, which is the pside 6, was kind of slow. That's why I decided to have it separated. And maybe the way I'm listening to the gamepad is not the most efficient one, but it works. It can be improved in later versions. One last thing, which I think is the most interesting part of having a gamepad script, is that you can visualize a monitor where you're doing a force spectroscopy course. So usually you scan an area, and then after the scan is finished, you take your time, you prepare your force spectroscopy, and then you select points, or you select a line, or you select a grid of points, or a volume of points where you want to do force spectroscopy. However, here with the gamepad, what we can do is we can move the probe using the joystick, and we can see in real time if the probe is on top of a structure that we want to analyze. So for instance, I took a scan of this area. Once I am happy with it, I put the probe away from the structure, and by clicking the button, one of the buttons, the AFM performs a force distance spectroscopy. Here it is. Now that I'm happy with the force distance spectroscopy, I can go to an area of interest, and I know that I am on top of the area because the color is exactly the same. So it's the same height, and I'm where I want to do the spectroscopy, and then I can trigger the spectroscopy. Well, I hope you enjoy this project and find it useful. If you want to know more, check our blog, and for more information, please check the description of the video. See you in another Friday AFM.